Welcome to the Deep Dive, your shortcut to expertise. Now, if you're an aspiring aviation maintenance technician, you might think the core of your job is, the big, complex stuff.
Right, like turbines or avionics.
Exactly. But actually, the most fundamental part of your career, day in and day out, really comes down to the hand tools in your box.
It's true. A huge chunk of your day involves using these tools, whether you're on a massive transport plane or something much smaller.
So this deep dive, it's specifically for you AMT General Course students. We're honing in on Chapter 11.
Yeah, our goal isn't just a list. We want to really distill the critical stuff: safety, proper care, how to store them, and maybe most importantly, the why behind choosing one tool over another. Like why a Phillips isn't a Reed and Prince. Mistakes there can be costly.
Our mission today is really about mastering these basics. Look,
Yeah.
we know later on you'll see some seriously specialized gear, hydraulic rigs, huge jigs, tools just for a 747. But you can't use those effectively or safely if you haven't mastered the fundamentals. It all starts here with the basics like a ball-peen hammer or a socket wrench. Misuse these and you risk damaging really complex, expensive components.
And that comes down to judgment, doesn't it?
Yeah.
Sound judgment, critical thinking. We're laying out the rules, the foundation, but good mechanics build on that with ingenuity, resourcefulness.
Knowing the limits is key.
Knowing the limits is absolutely the first step. That's what lets you be resourceful later.
Yeah.
Okay, so where should we start? Maybe with tools that involve a bit of force, kinetic energy.
Sounds good. Let's get into Section 1. Striking and turning tools. Hammers and screwdrivers. Okay, hammers and mallets. Controlled force. We've got the metal head types, ball peen, straight peen, cross peen, even the riveting hammer. How do you actually size these as a technician?
It's surprisingly straightforward. It's purely based on the weight of the head. That's it. The handle doesn't factor in.
It's just the head weight.
Got it. But honestly, where new techs often slip up isn't with the steel hammers. It's actually with the soft-face ones.
Ah, right. The ones made of wood, brass, lead, rawhide, rubber, plastic. Those are vital in aircraft work, aren't they? What's their specific role?
Their main job is shaping material gently and protecting surfaces you really don't want to damage. Think forming soft aluminum skins without creating sharp creases or dents.
Stress risers, basically.
Exactly, you want to avoid those. Or maybe tapping a component into place precisely, setting a rivet without heavy impact. That's their niche.
Okay, and that leads us straight to a big warning, right? The misuse of these soft-face tools, they aren't general hammers.
Absolutely not. You should never use a soft-faced hammer, especially plastic or rubber, to hit something hard like a steel punch head, a bolt, or a nail.
Why not? What happens?
You'll ruin the face immediately. You could embed metal chips in it or just flatten it, making it totally useless for the delicate work it was designed for. It's just a waste of a good specialty tool.
So selection is key, but technique matters just as much. If you're using, say, a ball-peen hammer for setting a rivet, what's the proper technique for safety and accuracy?
Good question. You need to think of your forearm as an extension of the handle. The swing comes from bending your elbow, not your wrist.
Okay, elbow, not wrist. Why?
It gives you much better control, more momentum in a controlled way, and lets you strike the target squarely with the full hammer face. A glancing blow doesn't work well and is way more likely to cause damage or bounce back unexpectedly.
And safety gear.
Oh, absolutely non-negotiable. If you're striking metal hammer on a metal tool like a punch, safety glasses or goggles are a must. Strongly encouraged is an understatement. Flying chips are a real hazard.
Good point. And keep the hammer face smooth.
Definitely. A chipped or rough face will just mar whatever you're striking. Keep them smooth.
All right, let's switch gears to maybe the most common tool for putting things together and taking them apart, the screwdriver. Seems simple, but selection is everything.
It really is. Its only job is loosening or tightening screws or screw head bolts. But pick the wrong size or type, and you're basically guaranteed to cause problems.
Okay, starting with the basic flat blade, the common screwdriver. What's the rule of thumb for fit to avoid that horrible slipping or cam out?
The blade needs to fill at least 75% of the length of the screw slot. And it needs to fit snugly widthwise, too.
75% minimum length. What if it's too small?
You'll just chew up the slot, burr it, mangle it. Then you're looking at needing a screw extractor, which wastes a ton of time. Or worse, the driver slips out entirely.
And damages something nearby, like the structure or wiring.
Exactly, which can be a much bigger problem than the screw itself. You see these flat blades used a lot on things like slotted cam lock fasteners on cowlings, for example.
Okay, now for a real point of distinction for an AMT student versus, say, someone working at home, recessed heads. specifically Phillips versus Reed and Prince. They look similar, but they are not the same.
This is absolutely fundamental. You have to know the difference visually. The reed and Prince head forms a perfect cross, sharp corners going right to the edge. It needs a screwdriver with a sharp pointed end to seat properly.
Okay, perfect cross, pointed driver, and Phillips.
The Phillips screw has that slightly larger, blunter center in the cross. It's not perfectly sharp. So the Phillips screwdriver needs a blunt end to match it.
So what happens if I grab that blunt Phillips driver and try to use it on a pointed Reed and Prince screw?
You're applying force only on the very tips of the screw's flukes instead of seating the driver fully. You'll just mangle both the screw head and the screwdriver tip. It won't seat right, and you'll likely strip it.
And they have different torque characteristics too, right?
Exactly. The Phillips is actually designed to cam out, to slip, when you apply too much torque. It's a feature to stop you from snapping the screw head off.
Whereas the Reed and Prince.
Because of its deeper, V-shaped grooves, it's designed for maximum torque transfer. It's not supposed to cam out easily. Using the wrong driver completely defeats the purpose of how that fastener was engineered. They are absolutely not interchangeable.
Critical difference. And we need to know the common sizes for Phillips too.
You do. The number 1 Phillips is for your smaller screw sizes 2, 3, and 4.
Okay, 1 for 2, 3, 4.
And the number 2 Phillips is the real workhorse. It covers screw sizes 5, 6, 7, 8, and 9.
So, number 2 for 5 through 9, those are the main ones.
Those are the ones you'll use constantly. There are bigger ones, number 3, number 4, but 1 and 2 are your daily drivers.
Sometimes the issue isn't the screw type, but just getting to it, access can be tight.
Oh yeah, that's where the offset screwdriver comes in handy. Both ends are bent at 90 degrees to the shank.
How does that help?
It lets you turn a screw where you have very little vertical clearance. You turn it a bit with one end, flip it, turn it a bit more with the other. It's slow, but it works.
And then there are the multi-tip drivers.
Right, the replaceable tip or 10-in-1 style screwdrivers. Very common now. You get flat, Phillips, maybe Torx, square drive tips, all in one handle. Very convenient for quick tasks.
We've mostly moved to cordless power screwdrivers now, haven't we? Replacing the old spiral types. But faster isn't always better if you're not careful.
That's a really important point. The speed is great, but it introduces new risks. It all comes down to the slip clutch setting on the power screwdriver.
The clutch is the safeguard.
It's the only safeguard. If you set that clutch tension too high when you're installing a screw, the tool just keeps driving. It doesn't know when to stop.
And then the tip slips.
Slips right over the screw head, destroys the recess. Now, you haven't just ruined the screw. You might have a partially installed fastener you need to somehow drill out. Big headache.
Okay, so that leads to a really critical rule for students. Do not use a regular cordless power drill with the screwdriver bit in it for screws.
Absolutely forbidden. Standard power drills, the kind you use for drilling holes, they usually don't have a proper adjustable slip clutch designed for delicate fasteners. They're built for high, continuous torque.
So what happens if you try?
Instant damage. You'll just deliver way too much force. You can mushroom the fastener head, gall the threads, strip the recess completely, or worse.
The tip jumps out.
Yeah, the tip jumps out and gouges the surrounding aircraft structure. That score mark is way more serious and expensive to fix than just replacing a screw. It can become a failure point. Don't do it.
Got it. And just some general misuse warnings for any screwdriver. We know not to use them as pry bars or chisels.
Right, and another big one.
Yeah.
Never, ever use a screwdriver to check an electrical circuit.
Why is that so bad?
The arc will burn and pit the screwdriver tip, ruining it for driving screws.
Ooh.
But worse, that heat could potentially fuse the blade to whatever you're checking, causing a short circuit or damaging the component itself.
And one final safety point.
Always secure small parts you're working on. Use a vise, clamp it to the bench. Don't hold it in your hand while using a screwdriver. If the tool slips, it's not just a damaged part, it could be a serious injury to your hand.
Okay, let's shift from striking and turning to tools designed more for gripping, maybe cutting wire, providing leverage. Pliers are a big category. What are the main types an AMT uses regularly?
You'll mostly see diagonal, needle nose, and duckbill pliers. Sizes usually range from about 5 to 12 inches.
Any specific uses for those, like round nose?
Yeah, round nose pliers are really just for light work, like crimping soft metal. You wouldn't use them for anything heavy that might spring the jaws. Needle nose are essential for grabbing small things or making tiny adjustments in really tight spots.
And duckbills, they have a very specific job in aviation, don't they?
They really do. Those wide, flat jaws are almost exclusively used for twisting safety wire. They give you that perfect grip and control you need for doing that job correctly.
Makes sense. And diagonal pliers. often called dikes.
Indispensable. They're short-jawed cutters, perfect for cutting and removing safety wire, but also for snipping cotter pins, small screws, even rivets sometimes.
Okay, now for maybe two absolutely critical rules about using pliers. Things every AMT student needs to internalize.
These are non-negotiables. Rule 1. Don't try to make pliers do more than they're designed for. Don't overload them, especially the long-nose types.
What happens if you do?
You'll spring the jaws, permanently damage them. They won't align properly anymore, won't hold tension. They're ruined.
And rule 2, the big one.
Rule 2, and this is huge, do not use pliers to turn nuts or bolts, ever.
Why is that such a hard and fast rule? It seems like a tempting shortcut sometimes if a wrench isn't right there.
It's a guaranteed way to mess things up. Pliers only grip a nut at two small points on opposite sides.
Not across the flats like a wrench.
Exactly. So they immediately start rounding off the corners of the nut. Once those corners are damaged, or buggered, as we sometimes say, you can't get a proper wrench on it anymore to tighten it correctly to the specified torque.
And a rounded nut is prone to slipping.
Prone to slipping often needs to be replaced immediately. It wastes time, wastes parts, and is just bad practice, especially on anything flight critical. Just don't do it.
Message received. Okay, let's talk about punches now. These seem pretty versatile, marking locations, starting holes, even removing stubborn parts.
They are versatile, and they're classified by the shape of their points, which tells you their job. Let's start with a prick punch.
Okay, prick punch sounds delicate.
It is. It has a very fine, sharp point. Its main use is making small reference marks, like when you're transferring dimensions from a pattern onto metal.
Yeah.
You just tap it lightly. It's not meant for heavy blows.
Got it. Light taps for reference. What's the next step up?
That would be the center punch. It's got a heavier body, and the point is ground differently, usually to a 60-degree angle.
And its specific purpose.
It's designed to make a bigger indentation, specifically to give the tip of a twist drill a place to start, so it doesn't wander or walk across the surface when you begin drilling.
Important for accuracy. Any warnings?
Yeah, don't hit it so hard that you seriously dimple the material or make it bulge out the backside. Just enough to create a starting point for the drill.
Okay, now for removing things, say a stuck rivet or a damaged pin, you mentioned using a sequence of punches. Which one comes first?
You start the removal process with a drive punch, sometimes called a tapered punch.
Drive punch or tapered punch? Why tapered?
It has a flat face for striking, but the body tapers all the way down to that face. Common sizes are maybe 18 to 14-inch wide. You use it to get the damaged rivet or pin moving initially.
But the taper can cause issues, right?
Right. As it drives the part out, its tapered sides will eventually start to bind in the hole. Once you've got it moving and the drive punch starts binding, you switch tools.
Just to what?
You switch to the pin punch, also known as a drift punch. This one finishes the job.
How is it different from the drive punch?
The key difference is the shank. A pin punch has a straight shank. It's not tapered. It's sized very precisely, usually in 1/32 of an inch increments, maybe from 1/16 up to 38-inch.
And the straight shank is important because
It won't spread the walls of the hole as it drives the object the rest of the way out. It just follows the object through.
Okay, drive punch first, then pin punch to finish. Now, you mentioned a safety rule about not using certain punches for removal.
Yes, absolutely critical. Never, ever try to use a prick punch or a center punch to drive something out of a hole.
Why?
Think about their points. They're sharp, designed to make indentations. If they hit one hard trying to relieve a pin, that sharp point will actually cause the end of the pin or rivet to spread outwards.
Making it tighter in the hole.
Exactly. It makes it bind even more firmly. You turn a relatively simple removal into a real problem. Always use the drive punch pin punch sequence for removal.
All right, let's move on to wrenches. Absolutely essential tools. We know they're usually made from tough stuff like chrome vanadium steel, pretty hard to break with normal use. Let's start with the basics. Open end versus box end.
Okay. Open-end wrenches, they have parallel jaws. And importantly, those jaws are usually set at a slight angle to the handle, typically 15 degrees.
That 15-degree angle isn't random, is it?
Not at all. It's designed that way. It gives you a bit of an advantage in tight spaces because you can flip the wrench over and get a new grip on the fastener without needing a huge swing arc.
Okay, so the angle helps with access. What about box end wrenches?
Box ends completely surround the nut or bolt head. They usually have 12 points inside.
12 points. Why is that significant?
Because with 12 points, you only need to swing the wrench 15 degrees to engage the next set of points on the fastener head. Again, really helpful in confined areas where you can barely move the handle.
Ah, so both types have features for tight spots. You mentioned flipping the open end. Is there a technique with the box end too?
Yes, exactly. It's
Yeah.
about inverting the wrench. If you're really cramped, you can only swing it 15 degrees. You turn the fastener that much, take the wrench off, flip it over 180 degrees, put it back on, and you get another 15 degrees of rotation.
So you can keep tightening or loosening it in tiny increments.
Precisely. It's much faster than using a tool that needs a 30 or 60-degree swing in those situations. And because box ends grip all around, they're ideal for breaking loose really tight fasteners without rounding the corners.
But maybe slower for spinning a nut off once it's loose.
Exactly. That's why the combination wrench is so popular. You get the best of both worlds. The strong box end on one side for breaking loose or final tightening, and the faster open end of the same size on the other side for quickly running the fastener down or off.
Makes sense. We also have ratcheting box ends now too, which speed things up.
Those are great. And of course, socket wrenches. These are really a system. The socket itself, which fits the fastener, and the handle or driver.
Lots of handle options there.
Oh yeah. T-handles, ratchets of various sizes, screwdriver grips, speed handles for spinning things fast, plus all sorts of extensions and universal joints to reach awkward places. They connect with that standard square drive lug held by a little spring-loaded ball to pop it.
Very versatile system. Now, what about the adjustable wrench, sometimes called a crescent wrench, kind of the utility player?
That's a good way to put it, utility player. It has one fixed jaw and one jaw that moves using a thumb screw. The opening is usually set at about 22.5 degrees to the handle.
And using this tool correctly involves one absolutely critical rule about how you apply force, doesn't it?
It does. This is non-negotiable for safety and for preventing damage. Always pull the wrench so the force is applied to the side of the handle attached to the fixed jaw.
Okay, pull towards the fixed jaw side. Why is that so important?
Think about how it's built. If you pull on the side with the movable jaw, all that force is pushing against the thumb screw mechanism that holds that jaw in place.
Which might have some play in it.
Exactly. Any little bit of slack or wear in that mechanism will allow the movable jaw to potentially open up slightly under load. When that happens, the wrench slips.
And rounds the nut.
Rounds the nut or slips off entirely, maybe causing you to hit your hand. By pulling on the fixed jaw side, you're using the solid, strong frame of the wrench to take the load. Much safer, much less likely to slip or damage the fastener.
Got it. Pull on the fixed jaw. Now, let's talk about some special wrenches vital for aviation work, especially around fluid lines. Crowfoot and flare nut wrenches.
Okay, the crowfoot wrench is interesting. It's basically like an open end or sometimes a flare nut end, but without a handle. It has a square drive hole so you can attach it to a socket extension or ratchet handle.
And why would you use that?
You use it to reach nuts on studs or bolts that are tucked away where a normal wrench just can't get maybe deep inside an engine compartment or behind other components.
Okay, access is the key there. What about the flare nut wrench? This one looks unique.
It does. It looks like a box end wrench that has a section cut out of the side, making it look like a C. It's also sometimes called a line wrench.
And that opening is crucial for its specific job.
Absolutely. It's designed almost exclusively for use on the B-nuts found on fluid lines, fuel, hydraulic, oxygen, pneumatic systems.
Why can't you just use a regular open-ended wrench on those?
Because B-nuts are often made of softer materials like aluminum or brass, and they connect tubing that can be easily damaged. A standard open-end wrench only grips 2 flats.
And can slip or deform the nut.
Exactly. The flare nut wrench, because it wraps further around, contacts the nut on 5 or sometimes even 6 flats. This gives a much better grip, allows you to apply the necessary torque without slipping, rounding the nut, or potentially distorting the tubing underneath it. Absolutely essential for fluid line work.
Makes perfect sense. We should also quickly mention spanner wrenches, hook, U-shaped, and pin types for those special round nuts with notches, and Allen wrenches, or hex keys, for internal hex socket screws and set screws.
Right. And that brings us to maybe the most critical precision fastening tools, torque wrenches. These are not just wrenches. They are delicate measuring instruments.
Their whole purpose is applying a very specific measured amount of rotational force or torque to a fastener, crucial for structural integrity.
Absolutely. Which means before you even think about using one, you need to give it a quick visual inspection. Look for any obvious damage. Is the pointer bent on a beam type? Is the glass cracked on a dial type? Does the handle look like it's been dropped or abused?
Because damage could affect its accuracy.
Definitely. And accuracy is everything. This is why calibration is so incredibly important.
How often do they need to be calibrated?
It varies by usage and manufacturer, but regular calibration is mandatory. Common intervals are maybe every 6 or 12 months. They drift over time or can be knocked out of whack if dropped.
And the consequences of using an out-of-calibration torque wrench.
Potentially catastrophic. If it reads low, you under-torque the fastener, and it could vibrate loose in flight. If it reads high, you over-torque it. You could snap the bolt, stretch the threads beyond their limits, or even damage the structure the fastener is holding together. Calibration is non-negotiable.
Okay, let's quickly touch on the three main types you'll encounter.
Sure. First, you have the deflecting beam type. It's simple, pretty robust. It has a pointer that moves along a scale as the main beam bends under load. You read the torque visually from the scale,
Second type.
the dial indicating type. This one also gives you a visual reading, but it's displayed on a round dial, kind of like a pressure gauge, often considered very accurate.
And the third, maybe the most common one seen in shops today.
That would be the micrometer setting type, often just called a click wrench. You preset the torque value you want by turning the handle, like setting a micrometer. When you pull on the wrench and reach that preset torque, you'll feel and usually hear a distinct click or impulse.
So it signals when you've reached the target torque, preventing over-tightening.
Exactly. Very useful for repetitive tasks where speed and consistency matter.
We should also give a quick mention to the strap wrench. Seems simple, but useful.
Invaluable in the right situation. A lot of aircraft components like filters, some tubing sections, or delicate fittings are round or irregularly shaped and easily damaged.
You couldn't use pliers or a pipe wrench on them?
Absolutely not. You'd crush or score them instantly. The strap wrench uses a strong fabric or sometimes a chain strap, often coated, to grip the component firmly, but without damaging the surface. Lets you turn things you couldn't grip otherwise.
Good tool to have. And finally, for those really stubborn fasteners that just won't budge with normal tools.
That's when you might reach for an impact driver. Not an impact wrench, but the handheld impact driver.
How does that work?
It uses a cam mechanism internally. You put the correct bit on the fastener, then strike the back end of the driver sharply with a mallet or hammer. That downward impact is converted by the cam into a sudden, high-torque rotational force.
Kind of a shock torque.
Exactly. That shock is often enough to break loose a fastener that's seized or over-tightened. But there's a critical warning here.
Which is?
You must use special heavy-duty bits and sockets specifically designed for impact use. Standard screwdriver bits or sockets will likely shatter under that sharp impact force. Use only impact-rated accessories.
All right, let's shift gears into cutting and shaping metal. Starting with hand snips. We have different types. Straight, curved, hawksbill, and the ones specific to aviation work.
Right, the aviation snips. These are really the standard for aircraft sheet metal. They're specifically designed to handle materials we commonly use, like heat-treated aluminum alloys and stainless steel.
What makes them different?
A couple of things. They often have compound leverage extra linkages in the handle, which multiplies your hand strength, making cutting easier. They usually have small serrations or teeth on the blades to grip the metal and prevent slipping.
And they can handle reasonably thick material.
Yeah, typically up to about 0.051 inches thick for aluminum alloy. And critically, they come in different cutting directions.
Left cutting, right cutting, and straight. Often color-coded handles.
Exactly. Green handles usually cut straight and right curves. Red handles cut straight and left curves. And yellow handles cut straight. Using the right direction helps keep the distortion on the waste side of the material, giving you a cleaner cut on the part you want to keep.
Now, there's a really important rule about finishing a cut made with snips. It's not a perfectly clean edge, is it?
No, it's not. Snips work by shearing the metal. They don't remove material like a saw does. This shearing action actually creates tiny microscopic fractures along the cut edge.
Which are bad, why?
Those fractures are stress risers. If you leave that edge as is on a part, especially a structural part, it's a potential starting point for a fatigue crack later on. Major safety issue.
So how do you deal with that?
The rule is, always make your cut with the snips about 1/132nd of an inch away from your final layout line. Leave a little extra material. Then you must finish that edge by removing that last 132nd inch using a file or sandpaper. You need to smooth it down completely to eliminate that fractured zone and create a safe, stable edge. Absolutely critical finishing step.
Got it. Cut shy, then file to the line. Okay, let's move to the hacksaw. A shop staple. But blade selection and how you install it are key.
They really are. First, installation. The teeth of the blade must point forward away from the handle.
Why forward?
Because the hacksaw only cuts on the push stroke, the forward stroke. If the teeth point backward, it won't cut effectively. Second, blade tension is crucial. It needs to be tight enough so the blade doesn't buckle or twist during the cut, which would make it wander off your line.
Makes sense. The standard blade size is usually 10 inches, right? And they come in different hardness types.
Yes, 10 inches common. You typically find all hard blades where the entire blade is hardened, good for cutting solid, heavy sections like tool steel or a thick bar stock. And then there are flexible blades where only the teeth are hardened.
Why use a flexible blade?
They're better for cutting things with thinner cross-sections, like tubing or angle iron, where an all-hard blade might be too brittle and snap if it binds.
Okay, but probably the most critical decision with a hacksaw is choosing the right blade pitch, the number of teeth per inch, or TPI. This seems like a place where mistakes are common.
Very common, and it makes a huge difference. The fundamental rule is you want to have at least 2 teeth, preferably 3, in contact with the material at all times during the cut.
2 or 3 teeth on the metal. Why?
If the teeth are too coarse, low TPI, for the material thickness, they'll straddle the edge instead of cutting it. They'll snag, jump, and you could strip the teeth right off the blade very quickly. If the teeth are too fine, high TPI, for thick material, the gullets between the teeth fill up with chips too fast, and the blade stops cutting efficiently.
So can you give us some guidelines for TPI selection?
Sure. For really thick, dense stuff like machine steel, cold-rolled steel, heavy structural sections, you'd use a coarse blade, maybe 14 TPI.
Okay, 14 TPI for thick solids.
For slightly less dense solid stock, like aluminum blocks, bearing metal, cast iron, 18 PPI is usually a good choice.
18 TPI for solid aluminum, cast iron.
Now, when you get to things with walls, like thick-walled tubing, pipe, channel iron, angle iron, you need finer teeth. Go with 24 TPI.
24 TPI for thick-walled hollow shapes.
And critically, for the thin stuff we often work with in aviation thin-walled tubing, sheet metal, you absolutely need the finest pitch, typically 32 TPI.
32 TPI for thin sheet and tubing. What happens if you use, say, 14 TPI on thin sheet metal?
Disaster. The coarse teeth will just hook onto the thin edge. They won't be able to cut properly, and you'll likely rip the teeth right off the blade on the first stroke. Match the TPI to the material thickness.
Got it. Only on the forward stroke.
Yes. Apply pressure only on the forward stroke. Lift slightly or release pressure on the backstroke. Use long, smooth, steady strokes. Aim for maybe 40 to 50 strokes per minute.
Not super fast then.
No. Rushing, using short, jerky strokes, doesn't clear chips well, and, more importantly, it generates too much heat from friction. That heat can ruin the temper of the blade teeth, making them dull almost instantly. Slow and steady wins the race with a hacksaw.
Okay, good advice. Let's talk about chisels now. These are for more aggressive cutting or shearing, usually made of tool steel.
All right, typically 8-sided tool steel bar stock. The cutting edge isn't perfectly flat. It's usually ground with a slight convexity, a gentle curve.
Why convex?
It strengthens the edge. It means the center of the edge takes the main impact from the hammer first, which helps prevent the more fragile corners from chipping or breaking off immediately. The typical cutting angle for general-purpose cold chisels is around 60 to 70 degrees, and you strike them with a ball-peen hammer, generally.
Okay, run us through the common types and what they're used for.
The most common is the flat cold chisel. It's your general-purpose tool for things like shearing off rivet heads, cutting thin sheet metal, or maybe splitting nuts that are seized onto bolts.
Flat chisel for general shearing. What else?
You have the cape chisel. This one is different because it has a much narrower cutting edge relative to its body width. It's used for cutting narrower grooves like keyways or for getting into square corners or slots.
Cape chisel for narrow slots. Okay.
Then there's the round nose chisel. As the name suggests, it has a rounded cutting edge, used for cutting semicircular grooves or channels like oil grooves and bearings or creating flails. It can also be useful sometimes for recentering a drill bit if it starts to wander off mark.
Round nose for curves. Anything else?
The diamond point chisel. This one has a point ground to a diamond shape. It's used for cutting V-shaped grooves or cleaning out sharp inside corners where other chisels can't reach effectively.
Got it. Flat. Cape, round nose, diamond point. Now let's move to the last tool in this section.
Yeah.
Files. Essential for finishing and shaving. How do we tell them apart? What are the key characteristics?
There are 3 main ways we classify files. First is by length. This is measured from the tip of the file down to the heel, which is where the main body ends before the tang, the pointy part that goes into the handle, begins. So length excludes the tang.
Okay, length is tip to heel. Second.
Second is by kind or coarseness. This refers to the spacing and size of the teeth. It ranges generally from rough, very coarse, down through bastard, second cut, and finally smooth, very fine.
Rough, bastard, second cut, smooth. Got it. And the third classification.
Third is by cut. This refers to the pattern of the teeth. The two main types are single cut and double cut.
Okay, what's the difference between single and double cut?
A single cut file has just one set of parallel teeth running diagonally across the file face, usually at an angle of 65 to 85 degrees. It gives a smoother finish, but removes material more slowly.
Single cut for smoothing.
Yeah.
And double cut.
A double cut file has two sets of teeth that cross each other. There's a coarser overcut at one angle, maybe 40-45 degrees, and then a finer upcut crossing over it at a different angle. This double pattern makes the file remove material much faster, but leaves a rougher finish.
Makes sense. Faster removal versus smoother finish. Now, there are many shapes of files, but which specific types should an AMT really know and understand their use?
Okay, definitely the hand file. What's special about a hand file is that it's parallel in width. It doesn't taper much side to side, but tapers in thickness. And crucially, it has one safe edge.
Safe edge, meaning?
One of the narrow edges of the file has no teeth cut into it. It's smooth. This is incredibly useful because it allows you to file right up into a corner on one surface without accidentally cutting or damaging the adjacent surface with the edge of the file.
Ah, very useful for inside corners. Okay. Hand file with a safe edge. What else?
The flat file is probably the most common general-purpose shape. It tapers slightly towards the tip in both width and thickness, usually double cut on the faces and single cut on the edges.
Flat file for general work.
The mill file is another important one. It's often single cut and is generally used for finer finishing work, draw filing, or working on softer metals where you want a smoother result. Also good for sharpening tools sometimes.
Mill file for finishing and soft metals. What about round shapes?
You need a round file, sometimes called a rat tail file. It's circular in cross-section and used for enlarging round holes or filing concave surfaces, like fillets. And closely related is the half-round file, which has one flat side and one curved side, making it versatile for both flat and curved surfaces.
Round and half round for curbs. Any other specialty files worth mentioning?
Yes, the Vixen file, or curved tooth file. These look very different. They have teeth that are milled in arcs across the face. They're designed specifically for rapid but smooth material removal on soft materials like aluminum, lead, brass, plastics, even wood. They resist clogging very well.
Vixen file for fast work on soft materials. Okay, we know the types. How about using them? There are different methods like cross-filing and draw-filing.
Right. Cross-filing is the most common method. You're pushing the file more or less straight across or slightly diagonally across the surface of the workpiece. Draw filing is different. You hold the file with both hands, one near each end, and pull or push it sideways along the length of the work.
What does draw filing achieve?
It produces a finer finish than cross-filing with the same file. The teeth create more of a shearing or scraping action when moved sideways. Good for final finishing or truing up an edge. And for rounding corners smoothly, you often use a rocking motion as you push the file forward, ensuring you use more of the file's length.
Okay, technique matters, but file care seems especially critical in an aircraft maintenance environment, right? Contamination is a big concern.
Absolutely huge. This requires real discipline. First, files should never be stored just tossed together in a drawer where they can bang against each other. That instantly dulls the teeth. They should be stored separately, maybe in a rack or wrapped.
Keep them separated. What else?
Keep them dry. Rust is terrible for the sharp cutting edges. And, maybe most importantly, keep them clean. The spaces between the teeth, the gullets, get clogged with filings, which we call pinning.
How do you clean them?
Tap the file gently on the bench first. But usually you need a specialized tool called a file card, which is like a stiff wire brush, to properly remove the embedded particles. You brush parallel to the teeth.
Why is a clawed or pinned file so bad?
Two reasons. First, a clogged file is essentially a dull file. It won't cut efficiently. Second, and critically in aviation, if those embedded filings are, say, steel particles from a previous job, and you then use that dirty file on an aluminum or magnesium part.
You're embedding dissimilar metals.
Exactly. You're introducing contamination that can set up galvanic corrosion down the road. Keeping files clean isn't just about performance. It's about preventing future material failures. Use the file card regularly.
Okay, let's talk about making holes. Drilling. In aviation maintenance, what types of portable drills are commonly used, and are there preferences?
We primarily use portable electric drills and pneumatic or air-powered drills. Both get the job done.
But is one preferred over the other in certain situations?
Yes, definitely. Pneumatic drills are strongly preferred whenever you're working around flammable materials or vapors. Think fuel tanks, hydraulic lines, areas with potential fumes.
Why pneumatic in those cases?
Because electric drill motors inherently create small sparks at the brushes during operation. In a flammable atmosphere, That spark could be an ignition source. Big hazard. Pneumatic drills run on compressed air, no sparks, much safer in those environments.
Makes sense. Safety first. Now, let's look closely at the twist drill bit itself. What are the key parts we need to know? The anatomy.
Okay, starting at the back, you have the shank. That's the part that goes into the drill chuck. It could be straight, which is common for hand drills, or sometimes tapered for larger drill presses.
Shank is for holding. Then the main part.
The body. This is the main working part, containing the spiral grooves called flutes. The flutes are crucial. They do two jobs. They provide channels for the cut material, the chips, to escape the hole, and they allow cutting fluid or coolant to reach the cutting edges.
Flutes for chip removal and cooling? What else?
Along the edge of the flute is a narrow raised strip called the margin, which helps keep the drill aligned in the hole. At the very tip, you have the conical point formed by the two cutting edges, often called the lips. The back edge of the lip is relieved slightly, called the heel, to provide clearance so only the sharp lip contacts the metal.
Okay, lips are the cutting edges. What about the angle of that point? Is it always the same?
Not always, but there's a standard. For general-purpose drilling in materials like steel and cast iron, the standard included angle between the two cutting lips is 118 degrees. That means each lip is ground at 59 degrees from the drill's center line.
118 degrees is standard for steel. What about other materials?
For softer materials like some aluminum alloys or plastics, you might use a sharper angle, maybe 90 degrees. For very hard or tough materials, you might use a flatter angle, maybe 135 degrees. But 118 is the common one to know.
Got it. Now, drill bit sizing seems confusing. There isn't just one system.
No, there are three main systems you need to be familiar with, and accuracy is key. First is the fractional system, where sizes are given in fractions of an inch, usually in increments down to 164th.
Like 14-inch, 38-inch, 764-inch.
Exactly. Second is the letter drill system. Sizes are designated by letters, running from A, smallest, about 0.234 inch, up to Z, largest, about 0.413 inch.
A to Z. And the third system.
The number drill system. This one uses gauge numbers, and it's actually the most precise for smaller diameters. It runs backwards from no 80, the absolute smallest, only 0.0135 inch, up to number 1, about 0.228 inch.
So 80 is tiny, 1 is bigger. Why 3 systems?
Historical reasons, mostly, but they allow for very fine steps in diameter, which is often needed for things like tapping holes or ensuring correct rivet shank clearance. You often have to convert between these systems or, more commonly, convert fractional or letter number sizes to their decimal equivalents because our precision measuring tools read in decimals.
Right, like micrometers. Okay, sharpening a drill bit by hand is a classic mechanic skill. Can you walk us through the basic steps for getting that standard 118-degree angle right?
It definitely takes practice to get good at it. The goal is to grind both cutting lips to be exactly the same length and at the correct angle, 59 degrees relative to the center line, and also to create the proper clearance behind the cutting edge, the heel.
Okay, so how do you start at the grinding wheel?
Right, you hold the drill bit so the cutting lip you're working on is horizontal and meets the flat face of the grinding wheel at roughly that 59-degree angle.
59 degrees to the wheel face. Then what?
As you lightly touch the lip to the spinning wheel, you perform a smooth combined motion. You slightly lower the shank end of the drill while also twisting the drill clockwise slightly on its own axis.
Lowering and twisting. What does that achieve?
Lowering the shank grinds the angle, and the clockwise twist creates that crucial heel clearance, making sure the cutting edge is the highest point. You grind just enough to sharpen the edge, stopping when you reach the heel. Then you repeat exactly the same process for the other cutting lip.
And checking your work is critical.
Absolutely. You need to use a drill point gauge to check two things. Are both lips exactly the same length? And is the angle correct, usually 118 degrees included? If the lips are different lengths or angles, the drill will cut an oversized, possibly crooked hole and wear out quickly because one lip is doing all the work.
Precision matters even in sharpening. Okay, so we've drilled a hole. What if we need that hole to be perfectly smooth and sized to a very exact dimension, maybe for a press-fit pin?
That's where reamers come in. Reamers are finishing tools designed to slightly enlarge a previously drilled hole to a precise diameter with a very smooth finish.
How much material can a reamer remove?
Very little. The hole needs to be drilled undersized first, but only by a tiny amount, typically just 0.0003 to 0.007 inches smaller than the final desired diameter.
3 to 7 thousandths undersize. Why so little?
Because reamers have very delicate cutting edges designed for light finishing cuts, not for hogging out material. Trying to remove too much stock will overload the reamer, likely chip the cutting edges, and result in a poorly finished, possibly oversized hole.
Okay, drill slightly undersized. Now, There's a fundamental rule about using reamers, isn't there? Something about rotation.
Yes, a critical rule. Always rotate a reamer only in the cutting direction, usually clockwise. Never ever rotate it backwards, even when removing it from the hole.
Never turn it backwards. Why is that so strictly enforced?
Because if you turn it backwards, the chips that are in the flutes get wedged behind the cutting edges. This instantly dulls or chips the delicate edges. Worse, it can cause the reamer to bind and chatter in the hole, leaving score marks or ripples on the finished surface, completely ruining the precise finish you were trying to achieve. Always turn clockwise, even when withdrawing it.
Got it. Clockwise only. There are different types of reamers too, right?
Yes, various types for different jobs: straight flute, spiral flute, which give a smoother cut, taper reamers for tapered holes, bottoming reamers for finishing the bottom of blind holes, and even expansion reamers that allow for slight size adjustment.
Okay, moving on from sizing holes to shaping their entrances. Countersinks. These are for flush fasteners.
Exactly. A countersink tool cuts a cone-shaped depression at the entrance of a hole so that the head of a flush head fastener, like a flush rivet or screw, will sit perfectly level with the surrounding surface.
Is there a standard angle for these in aviation?
Yes. The most common countersink angle used in aircraft work is 100 degrees, matching the angle found on standard AN and MS flush fasteners. You might occasionally see other angles like 82 degrees, but 100 degrees is the primary one to know.
100 degrees, and controlling the depth is important.
Crucial. If you countersink too deep, the fastener head will sit below the surface, and you've removed too much material, weakening the joint. If it's too shallow, the head will stick up, ruining the flush aerodynamic surface. For precise control, we often use stop countersinks.
Stop countersinks.
These have an adjustable collar or cage that rests on the surface around the hole and stops the cutting action at a preset depth. Some have micrometer adjustments, allowing you to set the depth down to the thousandth of an inch. Very precise.
Precision again. Okay, last items in this section. Taps and dies for creating threads. Taps for internal, dies for external.
Correct. Taps cut threads on the inside surface of a drilled hole. Dies cut threads on the outside surface of a round rod or shaft.
Let's start with taps. They usually come in sets.
Yes. For creating standard threads by hand, taps typically come in a set of 3 for each specific diameter and thread pitch, like 1420 NC, for example.
3 taps in a set. Why 3?
Because they progressively cut the full thread profile. The first tap used is the taper tap. It has the first 6 to 7 threads ground down significantly, making it easy to start straight in the hole. It doesn't cut a full thread depth initially.
Taper tap starts it, then?
Next, you use the plug tap. It has only the first 3 to 5 threads tapered. It cuts the threads deeper than the taper tap and is often sufficient for holes that go all the way through the material, through holes.
Plug tap cuts deeper. And the third one?
The third is the bottoming tap. This one has almost no taper, maybe just the very first thread or two slightly chamfered. Its purpose is to cut full-depth threads almost all the way to the bottom of blind hole, a hole that doesn't go all the way through. The taper and plug taps can't reach the bottom effectively.
So, taper, plug, bottoming a sequence for creating internal threads. Now, what about dies for external threads?
The most common type for hand threading is the adjustable round split die. It's a round die with the split on one side and usually a small screw across the split.
Why adjustable?
That screw allows you to slightly expand or compress the die, which gives you some control over the fit of the thread you're cutting, whether it's a looser or tighter fit on the mating part. You also have solid dies, which aren't adjustable, used more in machine threading. Dies are held in a die stock handle for turning.
And just like screws, threads come in standard types.
Yes. The common U.S. standards you'll encounter are National Coarse, NC, National Fine, NF, and sometimes National Extra Fine, NEF. You'll also see National Pipe Threads, NPT, which are tapered threads used for sealing fluid fittings. You need to match the tap or die to the specific thread standard required.
Okay, we've arrived at the tools that demand the utmost care. Layout and precision measuring instruments. Dropping these, even scratching them, can ruin their accuracy. Let's start with basic layout tools.
The foundation is the steel rule, or scale. They come rigid or flexible. You'll see them graduated in fractions of an inch, often down to 164th, or in decimal fractions, sometimes down to hundredths, 0.01 inch.
Just a basic measuring stick, but for more versatility.
The combination set is incredibly useful. It's based around a spiel rule, the blade, but has detachable heads you can slide along it.
What heads come with it?
Usually 3. First, the square head. It holds the blade at a perfect 90 degrees or 45-degree angle to an edge. It often includes a small spirit level and sometimes a removable scriber point tucked inside. You could also use it as a simple depth or height gauge.
Square head for 90s and 45s. Second head.
The center head, this is
Yeah.
V-shaped. When you place it against a round bar or shaft, the edge of the rule running through it precisely marks the center line of the cylinder. Very handy for layout on round stock.
Center head finds the middle of circles. And the third.
The protractor head. This one is semicircular, marked in degrees, 0 to 180. It allows you to set the blade at any angle relative to an edge, so you can measure existing angles or layout lines at specific angles. A very versatile layout tool, that combination set.
Okay, for actually marking lines on metal, we use a scriber. Looks like a sharp metal pencil.
Exactly. It scratches a fine, precise line onto the metal surface for layout. But there's a huge warning that comes with using scribers, especially on aircraft parts.
What's the warning?
You should only use a scriber where the line you make is going to be completely removed by the subsequent cutting or machining operation. Never leave a scribe line on a finished part,
Why not? It's just a tiny scratch.
because that tiny scratch acts just like the fracture zone from snips. It's a stress riser. It creates a weak point where a fatigue crack could potentially start later under operational stress. It's much safer to use a soft pencil or a layout fluid and scribe through that where needed, or use other marking methods if the line won't be removed. Avoid unnecessary scribing on structural parts.
Critical safety point. We also use calipers for measuring outside calipers for diameters, inside calipers for hole sizes, and hermaphrodite calipers. What are those for?
Hermaphrodite calipers have one leg, like an inside caliper pointed inwards or outwards, and one leg like a divider, sharp point. They're primarily used as marking gauges, like scribing a line parallel to an edge. They're not precision measuring tools. None of these spring joint calipers are really for getting exact numerical readings.
They're more for transferring or comparing sizes.
Exactly. For getting precise numerical measurements, especially down to thousandths of an inch, you have to use a micrometer.
Okay, the micrometer caliper. The workhorse of precision measurement in the shop reads much finer than a rule, right? Down to thousandths, even 10,000ths of an inch.
Correct. And as we mentioned, you absolutely need to be comfortable converting fractions to decimals to use a micrometer effectively, because the micrometer scale is decimal. The most common type you'll use constantly is the outside micrometer for measuring shaft diameters, material thickness, things like that.
Let's really break down how to read a standard non-digital outside micrometer. It seems intimidating at first. What are the main parts we look at?
Okay, you have the fixed parts, the U-shaped frame, the stationary handle at one end, and the cylindrical barrel, or sleeve, which has the main scale markings on it. Then you have the movable parts, the thimble, which rotates around the barrel, and the spindle, which moves in and out to contact the part being measured. The thimble has its own scale around its edge.
Frame, anvil, barrel, thimble, spindle. Got it. Now, reading the scale on the barrel and thimble, can we do it in stages?
Absolutely. Let's do it in 3 steps.
Okay.
Step 1, look at the long lines on the barrel. These are marked 0, 1, 2, 3, etc. Each number represents tenths of an inch, 1.10, 0.20, 0.300. Read the highest number fully visible.
Okay, read the last visible tenth. Step 2.
Step 2, look at the shorter lines on the barrel between the tenth marks. Each tenth of an inch space is divided into 4 smaller parts. Each of these small divisions represents 0.025 inches, 25 thousandths or 140th of an inch. Count how many of these 0.025 lancers are fully visible past the last visible tenth mark. Add that value, 0.025, 0.050, or 0.075, to your tenths reading.
Add the 25 thou increments. Step 3.
Step 3. Read the scale around the beveled edge of the thimble. This scale is marked from 0 to 24, representing thousandths of an inch. One full rotation of the thimble moves the spindle 0.025 inches, matching one small division on the barrel. Find the line on the thimble scale that aligns perfectly with the long horizontal index line on the barrel. Each mark on the thimble is 0.001 inch. Add this thimble reading to the sum from steps 1 and 2.
Okay, so it's C, last visible tenth, plus number of 0.025 lines visible by 0.025 plus thimble reading. A 3-part addition. Let's try an example. I see the 3 funny on the barrel, 0.310. I see 2 small lines past the 3, 2 by 0.025 equals 0.050. The thimble lines up exactly on the 12 mark, 0.012. So the total is 0.301 plus 0.012 plus 0.362 inches.
Perfect. That's exactly how you do it.
Yeah.
Practice makes it quick. Now, some micrometers have even finer readings.
The vernier scale for 10 thousandths.
Right. If your micrometer has a vernier scale, usually a set of lines etched vertically on the barrel above the main index line, you can read directly to 0.000001 inch. After getting your thousandths reading as we just described, you look at those vernier lines, find the one vernier line that aligns perfectly with any line on the thimble scale. The number of that vernier line, usually 09, tells you the digit for the 10,000th place. You just tack that digit onto the end of your thousandths reading.
So if the 7 vernier line lined up in our previous example, the reading would be 0.3627?
Precisely. It takes a good eye, but it adds that extra level of precision when needed.
Okay. And handling these tools, they're delicate.
Extremely. Never drop a micrometer. Don't over-tighten the spindle onto the workpiece. Use the ratchet stop or friction thimble, if it has one, to ensure consistent measuring pressure. Over-tightening can spring the frame, permanently ruining its accuracy. And just like torque wrenches, micrometers need regular calibration against known standards like gauge blocks or pins to make sure they read correctly, especially at 0.
Treat them like the precision instruments they are. Okay. Besides micrometers, what other key measuring tools do we rely on? Dial indicators and slide calipers come to mind.
Yes, a dial indicator doesn't usually measure an absolute size, but rather variations or changes in a surface. It has a sensitive probe or plunger that moves in and out, and this movement is mechanically amplified and displayed on a circular dial with a needle, or sometimes on a digital screen. Usually reads in thousandths of an inch.
What's a classic use for a dial indicator in aviation maintenance?
A very common application is checking shaft runout, or eccentricity. You'd mount the shaft securely, perhaps on V-blocks, then position the dial indicator so its probe rests against the shaft surface.
And then rotate the shaft.
Exactly. As you slowly rotate the shaft, you watch the needle on the dial. The total amount the needle fluctuates tells you how much runout or out of roundness the shaft has. You can also use it to check for flatness or warpage on surfaces like brake discs. The key is the indicator must be mounted rigidly. Any movement in the indicator itself will give you false readings.
Mount it solidly.
Okay.
Okay, and lastly, slide calipers. Often just called calipers, sometimes dial calipers or digital calipers.
These are extremely versatile and common. They offer much better accuracy than a simple ruler, typically reading down to thousandths of an inch, 0.001, for dial or digital versions, maybe hundredths, 0.01 now, 30 vandy for 1.
And they measure multiple things.
Yes, that's their strength. They have outside jaws for measuring diameters or thicknesses, inside jaws for measuring the width of holes or slots, and often a thin depth rod that extends out the end for measuring the depth of holes or steps. Very handy, rugged tool for quick, reasonably precise measurements on the shop floor. Hashtag outro.
Wow, that was a really thorough tour of the essential hand tools and measuring devices from Chapter 11. I think the big takeaways for AMT students really boil down to careful selection and disciplined use, right?
Absolutely. It's about knowing the visual difference between a Phillips and a Reed and Prince, understanding the mechanics like pulling on the fixed jaw of an adjustable wrench, adhering to those critical material rules, like only turning a reamer clockwise or always filing away that fracture zone left by snips.
It's all about precision and preventing damage.
Exactly. Every single point we discussed, whether it's the 15-degree flip of a box end wrench or drilling a hole only 3 to 7 thousandths under size for reaming, it's all geared towards doing the job correctly, minimizing wear, and eliminating any chance of causing a failure in a component that's critical to flight safety. You can have great hands-on skill, but without this foundational knowledge, it's not enough.
And we spent a good amount of time stressing the absolute need for calibration on tools like torque wrenches and micrometers. The integrity of the aircraft literally depends on those measurements being accurate.
It really does. Which leads us to a final thought, something for you listeners to chew on as you continue your studies.
Okay, let's hear it.
Given how much we emphasize the need for careful reading and calibration of traditional mechanical measuring tools, think about the increasing use of digital readout devices, digital micrometers, digital calipers, digital torque wrenches. On the surface, they seem simpler, right? No interpreting scales.
Just read the number.
Exactly. But how might this shift fundamentally change the AMT's workflow in the future? Does relying on a digital display make things truly simpler? Or does it introduce new complexities? Think about battery dependence, potential software glitches, the need for maybe even more frequent electronic calibration checks compared to robust mechanical tools. Will digital ultimately simplify the AMT's measurement tasks, or just trade one set of required skills and vigilance for another? Something to consider.